Okay, thank you very much for the invitation to present today. What I'm going to show you is essentially an empirical work. There's not much simulation or anything, although I have a background in physics and dynamical systems. Like here, I'm only showing empirical results. So basically, what I'm going to show you is that cardiac activity can be synchronized across subjects when the subjects are attentive to the external stimulus, to a naturalistic story, and then this could be relevant for clinical purposes. So basically, let's go here. When I talk about consciousness, because like this is a difficult word in terms of definitions, most people tend to work either in what we call conscious content, which is basically being able to understand what's going on your minds, on your brains, when you're aware of something in particular and you can report that. So basically, you could see here like the train either going in or outside the station, and I could measure in your brains what's going on when you switch with one person to the other, understand what's related to a particular content. But what I work the most is in the definition of conscious state, and it's related to the system and what are the properties of that system that allow the person in particular to be conscious of the external world independent of the content. And this is an important question in some clinical conditions such as sleep, which is normal, anesthesia, which is induced, or the pathological condition, which is called disorders of consciousness. In this case, what we measure is responsiveness, which is basically the capacity of the subject to say to us, yes, I'm aware, yes, I can see you, or I can have a conscious experience. And when it comes to these patients, it's important to define a diagnosis, because when we differentiate between minimally conscious state or vegetative state, that changes everything in terms of the ethical considerations, and on top of that, the family needs to know, and the doctors, whether the patient is conscious or not. So, like I said, this becomes like both a fundamental and applied question. Fundamental because we can try to understand how consciousness works in the brain, and in particular, like applied because like that doctors and families need to know whether the patient in particular is conscious or not. So there are different research lines in my lab. What I'm going to work to discuss today is brain-body interactions, which is basically the capacity of the body to respond to a conscious processing in the brain. So how the brain-body interactions tend to work? Well, the external world is processed by our brains, and there is some internal activity that reflects into the brain, and also an internal a feed of information coming from the external world. But the reality is that the brain controls all the autonomic system. The autonomic system is associated to different activities that we are not aware of, such as the heart activity, the respiratory activity, all the digestive system. And this autonomous system is a control system. It's essentially unconscious. We are not aware of when our heart beats, and regulates our principles or our functions. So we had some preliminary results linking the autonomous nervous system and cognition. In a study published in 2017, we already showed that patients in vegetative state have their cardiac cycle completely independent of the external stimulus. And when you put these patients in a situation of trying to detect a global regularity in auditory protocol, the cardiac activity doesn't change at all. On the other hand, when we talk about minimally conscious patients, these are patients that have some sort of conscious experience. They have a phase reset whenever they detect this type of regularities violations. So this is very important, because using a signal which is very easy to obtain, which is the cardiac activity, we were able to differentiate between patients that were unconscious from patients that were conscious. But this is just like at the single subject level, seeing some sort of reset on the cardiac cycle, but that's not related to the fact that whether the subject is aware or not of this irregularity or anything. So for that, we wanted to do something slightly different. And we were based on previous results of inter-subject synchronization and cognition. And they are like very important results, first of which is the work of Uri Yazon that shows that the brain synchronizes when we watch a movie, and that synchronization is much, much higher when the movie is engaging. So basically, it's not the same thing to watch a movie related with emotion and with high impact images to reality footage from a square, which has no sort of like attention effect on the subjects. So that was like a very important first result. Then there was like interesting result for us as well related to patients in disorders of consciousness. Here they show that this is coming from the group from Adrian Owen. Here they show patients with a small movie from Hitchcock, and what they show is that the patients were even if they were vegetative, they had a synchronization of the brain activity in fMRI that was related to the healthy participants, and those patients, in fact, they were having what we call consciousness, but without movement. So it's an association between cognition and motor output. So that is with fMRI, and also there's interesting results with EEG. This is coming from the work of Lucas Parra. In this case, they show different videos, and they ask the patients, the subjects in this case, to either pay attention to the videos or not to pay attention to the videos. And in one case, they were like engaged with the videos. In the other case, they were either like paying counting from 7 steps from 1,000 backwards. So it's something that you do simultaneously while you pay attention, while you look at the video, and then this sort of like draws attention away from the video. And this is interesting because when the subjects were not paying attention, the synchronization as a group, and then the measure is called inter-subject coherence, drops dramatically. So you see that systematically each individual has a smaller similarity to the group when they're not paying attention to the video. So that's quite good, and this is coming from the brain, and which in principle is where consciousness occurs. But what happens with the other physiological signals? Can we see something similar? So how do you measure heart rate synchronization across subjects? So what we propose is that you cannot use the raw signal, because I don't care whether you are a person has a higher rhythm than the other. What I care of is that whether these people, this group, in fact increases or decreases the heart rate at the same time. So basically, does the emotion on the movie like makes you your heart beat faster or slower independently of your basal condition? So basically what you're seeing here is a pipeline of analysis, and what you see is the original EKG from a subject, and what we detect is each heartbeat, and in between heartbeats you can compute the instantaneous heart rate, which is basically the inverse of the period between two heartbeats, and you see that there is some sort of variance between heartbeats. It's not completely regular, and in fact the irregularity is a measure of sanity in the cardiovascular system. So I can measure the instantaneous heart rate, and this is what you see on the bottom figure. And then we can interpolate the signal in between samples, and you can get a continuous signal of instantaneous heart rate. So once you have that, it's straightforward to compute Pearson correlation among subjects between the group, and that's the panel on the C space. What you see here is 27 subjects and the correlation among them, and what you see is that the images are mostly on the positive domain, so the correlation tends to be biased towards positive values, and that's basically what we predicted, because basically you see a significant correlation among subjects, so individuals. You have all pairs of correlations here. So finally what we do is to reduce one dimension on this symmetric matrix, and you end up with a value per subject, which is basically the similarity of that given subject to the rest of the group. So what you see here is one segment of 1 minute of data, and you see a distribution of values which is clearly above 0. So let me show you 4 experiments and try to interpret those experiments. So basically, the first experiment is just simply a subject's listening to a story. It's 20,000 Leagues Under the Sea, the Jules Verne's novel. And these are 16 epochs of 1 minute. So basically 60 minutes of recording. And what we measure, basically, it's the inter-subject synchronization of the heart rate for the individuals for each segment. And what you see is that just a few of them are significant when you compare to the permutations, where the permutation in this case, the permutation test is by doing a surrogate of the data circularly shifting all the subjects. So basically you lose the temporal synchrony across subjects, and you end up with a value that's a null result, and then you can compare the individual subject to this null result, and you end up with that in each segment of 1 minute that only just a few subjects are significant compared to the surrogate. But when you average across the 16 segments, you end up with that we found that 16 out of the 27 subjects have a significant correlation to the group. So basically what we see is that in fact there is a significant correlation. The size effect is not huge, but it's systematically observed. And in this case, there's no modulation of attention. It's just the subjects listening to the story. So we don't know whether they are paying attention or not. So this is something to control too. But this is an interesting first result. And the second result is that you can do exactly the same thing, which is in panel C, but permuting the segments. So basically comparing each subject to the segments of to the other segments. And when you do that, you end up with almost a 0 correlation. So basically, if I compare the cardiac activities of one subject to the other subjects on the other segments, you end up with 0 correlation. So systematically increase of the intersubject coherence when you compare the data within segment or across segments. So this is a very interesting first result. The second result is using data from Lucas Parra in New York. It's the same data that he used on EEG, but in this case using EKG. So basically what we have is the subjects either paying attention to the story or counting backwards. So what you see is that systematically the individuals have a decrease on the cardiac synchronization to the group when they were paying attention to the story. So that is exactly what we predicted. Here, what you're seeing is the 5 stories used on the original study, and systematically there is a decrease on the synchronization when you're paying attention to the story. When you average the 5 story, this result becomes even stronger. So you see that even though you might find some synchronization for the distracted condition, the synchronization is much more robust when the subject were in fact paying attention, and this is quite important. So this was the first demonstration that with attention, with the fact that the subjects were paying attention to the story, there was a strong result in terms of synchronization. We then checked whether this was related to the respiration, because we know that respiration can modulate, can train cardiac activity, and respiration can be modulated consciously. And in fact, if you do the same thing with respiration, you don't find a result. In fact, we were expecting to have a result because there is a heart rate respiratory correlation. So basically, when you are on the trough or valleys of the respiration, there is an increase or decrease on the cardiac activity. But when you do the correlation of the respiratory activity on these subjects, you find no effect, no modulation of the synchronization of the respiration when you compare attention versus distraction. So at least in this data, respiration doesn't seem to explain our results. We also have a result related to memory, because what we had is a questionnaire that we play to the subjects, we gave to the subjects, even after the attentive or the distracted condition, and then the performance to fill the questionnaire was much higher on the attentive versus distracted condition, because in the distracted condition, they were like heavily affected by the ongoing second task. So they were not as good to measure, to pay attention to the story. So what you see, again, this is a second data set. This is not the data set from New York. This is the data set that we acquire in Paris in a very similar fashion that the one in New York. And we basically were able to replicate the results. But in this case, we also added the questionnaires. And what you see here on the y-axis is the memory performance of the subjects. So basically on the distracted condition, you see that the memory performance is only up to 70%. And what you see, is that there is no relationship between the memory performance and the correlation of the cardiac activity. On the other hand, there is a significant correlation. It's not traced here because it's a nonlinear relationship between the IAC, the inter-subject correlation, and the memory performance. So the better your performance was, the better your synchronization was to the group. So that sort of like relates to your capacity to extract information from the story that the subjects were listening to. So our last analysis was in these patients that had disorders of consciousness, and what we observed is that first of all there was a significant difference between the healthy participants and the patients with disorders of consciousness. So basically, you see a stronger synchronization of the healthy participants within the group, versus when you compare that with the disorders of consciousness patients. Here you observe patients either in coma, unresponsiveness, wakefulness syndrome, which is a vegetative state, minimally conscious minus, which is non-responsive, minimally conscious plus, which is people with capacity to respond, and exit MCS, which is the higher state. So you observe here two values, in fact, were the highest values observed on the patients. And in fact, these were the only two patients that recovered consciousness afterwards. So these were the two patients who were more similar in terms of synchronization to the healthy participants. So basically, these two guys, the only ones who had a significant correlation were, in fact, the ones that recovered. And in fact, when you measure the DTI, so this is the using MRI, structural MRI, when you measure the goodness of their tracks, so the fibers on the brains of this patient, a measure which is highly representative of the capacity of the subject to recover, you see a very strong correlation between the FA index, which is this indemnity of the structural connectivity, to the capacity to correlate to the healthy participants. So basically, the more you are similar to the healthy participants, the more your brain has a sane or a structural pattern that resembles a healthy brain. So with that, this is the end basically of the experimental results. So in conclusion, we found an intersubject synchronization of the cardiac cycle during naturalistic simulation. We found also that this synchronization is modulated by attention and conscious processing of the stimuli. We also show a proof of concept of the application in disorders of consciousness. And our next step is try to understand where this synchronization is coming from, how the brain basically kicks this oscillator to put it in synchronization. Whether this is sort of indirect or not, whether the subjects are somehow like more or less aware of the cardiac activity, because there is a strong literature regarding the introspection, which is basically the capacity of the subjects to read their internal organs, and whether this is somehow like related to the results that we observe. So thank you very much for your attention. I have to mention that this was a work done essentially by Pauline Perez, a PhD student in my lab, and also the collaboration of Jan Mansen, a postdoc in Luca's lab, which is also a senior author of this paper, and other collaborators that have been working on during the last years. Thank you very much for your attention. Thank you.
I suppose the saddest part about this is that you can't hear all of us clapping, but I'm sure everyone who is watching is clapping. That was a very nice talk, Jacobo.
Thank you.
And perfectly, we still have 5 minutes for questions. So Omkar sent a question through the Q&A. Maybe I'll allow Omkar to speak. Omkar, you are able to speak right now. If you unmute yourself, you can ask your question in person.
Yeah, so my question was how the experiment 3 about ISC predicting the memory was designed.
Okay, let's go back to the slide. So in this case, this was a new data set. Experiment 2 was data already acquired for the original paper of Lucas in EEG. In this case, what we had is we had 4 stories, and the subjects here either story 1 and story 2 in the attentive condition, and story 3 and story 4 in the distracted condition. Okay, and then the other half of the subjects had story 1 in the non-attentive condition, and story 1 and 2 in the non-attentive condition, and story 3 and 4 on the attentive condition. So it's counterbalance. So you have half of the subjects listening to story 1 and 2 attentive, the other half distracted, and vice versa with story 3 and 4. So what's the attentive condition? Basically, you tell the subjects, pay attention to the story. There will be a questionnaire afterwards. And then what's the distracted condition? In the distracted condition, what you have is the story, but there are also tones on the background. So either you have like low tones and high tones, and what you have to do is to count the low tones in between high tones. This is a very demanding task. And basically, we ask the subjects to report the number of the maximum number of low tones in between high tones. And then we give the questionnaire anyway to the subjects on the non-attentive condition. So you can compare this condition of the subjects when they were paying attention to the story and not paying attention to the distractive tones on the background, or they were paying attention to the distractive tones and not paying attention to the story. Importantly, the story is synchronous, always synchronous across subjects, and the tones are asynchronous. So basically, the tones cannot entrain a synchronization between subjects because they were different for all subjects. I'm not sure that answers your questions, but I think I give a detailed explanation of how we did it.
So we still have a little bit of time. Does anybody have any other questions they would like to ask? Okay. Well, I think I speak for all of us. I say thank you very much, Jacobo, for that very interesting and stimulating talk. Very, very well done.
Thank you very much.